Recrystallization is a technique used to purify solid organic compounds which may contain impurities. It involves the dissolution of an impure solid compound in a hot solvent. Ideally, the hot solvent dissolves the desired compound and the impurities, but when cooled, the pure compound crystallizes out of the solution while the impurities remain dissolved. Slow cooling is important because rapid cooling causes impurities to be trapped within the crystal lattice as they form. Solvent selection is the first step in recrystallization. If the ideal solvent is not known, it will need to be determined experimentally. Remember, a good solvent is one that, at hot temperatures, dissolves most if not all components of the impure solid mixture, and at cold temperatures, does not dissolve the desired solute, but does dissolve the impurities. To begin exploring potential solvents, place approximately 10 to 20 milligrams of the impure solid in a test tube. Add about 0.5 milliliters of solvent to the tube and swirl. If the solid dissolves at room temperature, this solvent is not appropriate for recrystallization. If the solid does not dissolve, check if it dissolves at a higher temperature by heating the solution to a gentle boil for about 1 to 2 minutes. If the solid dissolves, this solvent is likely appropriate for a recrystallization. To summarize, a good recrystallization solvent should not dissolve the desired compound at room temperature, but should dissolve it at hot temperatures. Note that a mixture of two different solvents may be ideal for some compounds. Experimentation or reference to text will be required to find the mixture of solvents. When a suitable solvent is found, proceed with the recrystallization. The most important factor for a successful recrystallization is adding the minimum amount of hot solvent required to dissolve the sample. As such, both the solvent flasks and the sample flask should remain hot throughout the procedure. For this demonstration, a mixed solvent system of ethanol and water will be used. For a 0.6 to 0.7 gram sample of impure compound, prepare about 50 milliliters of the selected solvent in an Erlenmeyer. In general, beakers should not be used to heat solvents because they accelerate evaporation and the fumes released are more easily combustible compared to using Erlenmeyer flasks due to their conical shape. Heat the solvent gently on a hot plate to just below the boiling point of the solvent. Note that organic solvents are flammable, so open flames should not be used. Place about 0.6 to 0.7 grams of the impure compound in another Erlenmeyer flask. It is important that an Erlenmeyer is used instead of a beaker, as it will minimize the formation of crystals up the wall of the flask. Recrystallization involves dissolving the sample in a minimum amount of hot solvent. Add about 1.5 milliliters of ethanol to the sample and begin warming on the hot plate. If the sample dissolves upon heating, do not add more solvent and remove the hot solution from the hot plate. You can confirm that all of the solids have dissolved when the remaining solution is clear, but not necessarily colorless. If the solids have not dissolved, very slowly add water, about 1 milliliter at a time, to a maximum of 10 milliliters. If the solid still has not dissolved, add more ethanol, 1 milliliter at a time, to a maximum of 5 milliliters. Once the solid has dissolved, stop adding solvent and remove the flask from the heat. Note that if there are insoluble impurities, do not add excess solvent to dissolve them. Most recrystallizations only require one solvent. In this case, the flask containing the desired solvent and the sample flask should be heated simultaneously on a hot plate. Then, the minimum amount of hot solvent should be added to fully dissolve the sample. Why is the volume of solvent important? If too little solvent is used, the solution will be too concentrated and the sample will not dissolve. This will lead to an incomplete purification. If too much solvent is used, the solution will be too dilute and the product will not recrystallize. When adding the solvent, it is better to stray towards adding too little solvent because more solvent can always be added while heating the solution. On the other hand, removing solvent when there is a great excess is not as simple.
If the solution is free from insoluble impurities and unexpected coloration, proceed to the crystallization step. Otherwise, the insoluble impurities and unexpected coloration will need to be removed. Insoluble impurities will simply be removed by hot gravity filtration. Colored impurities will first need to be removed using a decolorizing agent, then by hot gravity filtration. Activated charcoal is a decolorizing agent used to remove colored impurities from the sample. It is made of very finely divided carbon with a high surface area to absorb the impurities. Remove the flask from the heat and allow it to cool for 1 to 2 minutes to prevent foaming when the charcoal is added. Add a small amount of activated charcoal to the solution and swirl. The solution should turn gray or black. Gently heat the solution while swirling. After a few minutes, perform a gravity filtration to remove the activated charcoal. Prepare for the gravity filtration by setting up a ring clamp on a retort stand. Place a folded filter paper inside a stemless funnel on the ring clamp. This filter paper may be fluted to increase surface area. Place a clean and dry Erlenmeyer flask directly below the funnel and pour the hot solution through the funnel and allow the filtrate to collect in the receiving flask. Wash the filter paper with a minimal amount of hot solvent to prevent the formation of crystals on the filter paper. Allow the hot solution to slowly cool to room temperature for about 5 minutes. Then clamp the flask in an ice water bath for another 5 to 10 minutes to allow the pure compound to crystallize. Patience is important in this step in order to obtain pure compound. If no crystals form, scratch the bottom of the flask with a thick glass rod. This may promote crystallization as a thin glass etch can provide a surface for which the crystals can form on. If crystals still do not form, seed the solution by adding a few small crystals of the original compound. Again, this provides a surface for the crystals to form upon. Now that the crystallization is complete, the pure crystals can be separated from the solution by vacuum filtration. Obtain a Hirsch or Buchner funnel and place filter paper to cover the holes of the funnel. Attach a neoprene adapter to the bottom of the funnel and insert it into the top of a clamped filter flask. Attach thick-walled vacuum tubing to the filter flask and turn on the vacuum. Dampen the filter paper with a small volume of cold solvent to create a better seal between the filter paper and the funnel. Pour the solution containing the crystals through the funnel and rinse the flask with ice-cold solvent to transfer any remaining crystals. Allow the crystals to vacuum dry for about 5 minutes. Turn the vacuum off and transfer the crystals from the funnel onto a pre-weighed watch glass. Allow the crystals to air dry for 10 to 15 minutes. The product can now be weighed and analyzed to determine purity.
To briefly review, here are the steps of recrystallization. Find an appropriate solvent. Dissolve impure compound in minimal hot solvent. Filter insoluble impurities and decolorize if necessary. Recrystallize by slow cooling. Filter to isolate purified crystals.